All right, in this part of the lecture, we're going to talk about the technical details of actually setting up GANs. So this is the outline of the GAN algorithm that we saw before, and we'll dig into this a little bit more. So the classic GAN described by this procedure can also be expressed as a two-player game, as a min-max problem, where you have two players, G and D, the generator and the discriminator, and these two players are respectively trying to minimize or maximize the same objective. So they have the same objective, but G is trying to minimize it, whereas D is trying to maximize it. And that makes a lot of sense. They're competing with each other, so it would make sense that they would aim to go in opposite directions on the same objective. And the objective is basically the discriminator classification objective. So this expression that I have written out here, it might look a little bit complex, but it's basically just cross-entropy loss. Remember that cross-entropy loss is just take the positive labeled images and maximize the log probability of the positive label, and then take the negative labeled images and then maximize the log probability of the negative label. Now, in a binary classification problem, the probability of the negative label is just 1 minus the probability of the positive label, so that's why for the second term you have 1 minus d. Okay? So this is just the cross-entropy loss. Maximize the log d on the data, and then maximize log 1 minus d for the generated samples. And both of these are expected values. So the first expected value is over the training data, and that's just approximated by averaging over all of your training points. Remember that averaging a log likelihood over training points is just an approximation, a sample-based approximation to the expected value over the training distribution, which we're calling p-data here. The second expression is just averaging together log of 1 minus d over xj, where xj's are generated images. So the reason that it's written as an expectation over z is because the way that you get xj is you generate z from p of z, and then you run it through g. Okay? So there's two expectations, but the way that we calculate them in practice, for the first one, we average over the training set. For the second one, we generate a bunch of random z's, take their corresponding x's, and then average over those. So D is trying to maximize this quantity. It's trying to maximize log likelihood, which means minimizing cross-entropy loss. G is trying to minimize it. It's trying to minimize the likelihood for the discriminator, which is the same as maximizing the discriminator's cross-entropy loss. Basically make it hard for the discriminator to tell that its images are in fact fake images. Okay? So this way of writing the GAN as a min-max problem is much more concise, and then the procedure at the top is just the algorithm we use to solve this min-max problem. So it is no longer a conventional gradient descent optimization. It is in fact the problem of finding the Nash equilibrium in a two-player game. Okay. All right, so here is the GAN game, and I've written it now in terms of theta and phi, where theta is the parameters of G and phi are the parameters of D. So it's exactly the same as before, only now it's a min over theta, max over phi, just to emphasize that we have parameters. And the algorithm is basically the same as alternating between a gradient ascent step on phi, because phi is maximizing, and a gradient descent step on theta. And these two steps just alternate, and that's basically the entire algorithm. Okay, now there are two important details that we have to get right in order for this to work. First, how to make this work with stochastic gradient descent or ascent, right? Because we want to use a mini-batch. And second, how do you actually compute the gradients? But both of these are actually pretty simple. So for using stochastic gradient ascent or descent, we approximate the gradient by using a mini-batch of training points for the first expectation. And then for the second expectation, we sample the same number of z's and run them through the generator. And that basically gives us a mini-batch gradient ascent or mini-batch gradient descent version of this for phi and theta, respectively. So that's pretty straightforward. And again, the loss for the discriminator is just the cross-entropy loss. Technically, it's the negative of the cross-entropy loss because we're doing ascent, or you could do descent on the cross-entropy loss, and it's exactly the same. And then the generator loss is just estimated with the same mini-batch of z's. Just run them through the generator, ask the discriminator what probability it lends to them, and then use that as the loss for your generator. Okay. So actually computing these gradients is generally pretty straightforward. So the gradient for the discriminator, and it's just cross entropy loss, all the backprop stuff from before applies. The gradient for the generators may be a little bit more elaborate, because computing the loss function for the generator requires generating images and then passing them into the discriminator. So the way that we calculate gradients for the generator is we backpropagate through the discriminator into the generator. So this expression here is the loss function for the generator. We're going to backpropagate through the discriminant with respect to its inputs, and that will give us dl dx. And then we can backpropagate that through the generator, which will give us, via the chain rule, dx d theta times dl dx. And that's what we want. So in practice, all you have to do is just construct one graph in your automatic differentiation software, which consists of the concatenation of G and D, and then the regular backpropagation autodiff operation will calculate the gradients you need through that graph. Okay, so that's all pretty straightforward. Gradients for the discriminator, very easy, just like a regular classifier. Gradients for the generator, easy to get just by composing the generator and discriminator and using your favorite automatic differentiation software. Okay, so that's basically all you need in order to implement a basic GAN. Now let's talk about a little bit of a theoretical question. Okay, so we saw how the GAN can be constructed. We got a little bit of intuition for why a GAN should match distributions. But what particular objective does the GAN actually optimize? Can we somehow take this two-player game, analyze it, and be able to state formally that at convergence, this should minimize some measure of discrepancy between the data distribution and the distribution of images produced by our GAN? So here's how we can do this. What can we say about G of Z at convergence? Well, it's a little bit hard to do this because Nash equilibria are very hard to work with. So how about we instead aim to simplify this two-player game just for the purpose of theoretical analysis by expressing the optimal d of x in closed form as a function of G. Right? We have an outer minimization and inner maximization. So maybe that inner maximization over D, maybe its solution can be expressed in closed form as a function of G. We obviously can't implement that in code. We need to actually train a neural net to do that. But maybe at least theoretically we can characterize the solution for max D as a function of G. So a very useful property for this is an identity that can be used to describe the Bayes optimal classifier. So here's how we can derive this. Let's say that we have a set of positively labeled images, dt, and a set of negatively labeled images. Now let's say the positive labels come from P of x, and the negative labeled images come from Q of x. So Q of x is the distribution over images with a negative label, and P of x is the distribution over images with a positive label. In the case of a GAN, P of x is P data, and Q of x is the distribution over images obtained by sampling Z from P of Z and then running that through G. Okay. So the optimal discriminator, which I'm going to call D star, is just the argmax of the log likelihood, or equivalent, the argmin of the cross-entropy loss, which we can write as the expectation under P of log D, because P is the distribution over images with a positive label, plus an expectation under Q of log 1 minus D, because Q is the distribution over points with the negative label. So now what we're going to do is we're going to take the derivative of this with respect to D. So we're not taking the derivative with respect to any parameters, we're just actually taking the derivative with respect to the function D. And we're going to set that derivative to 0 and solve for D. So that's usually what you do if you want to find the max or the min. Okay? So the derivative of the log D is 1 over D. The derivative of log 1 minus D is minus 1 over 1 minus D. So that's how we get the derivative, expectation under P of 1 over D minus expectation under Q of 1 over 1 minus D. And if we can solve for the D that sets this to 0, we will have recovered the optimal discriminator. Now, crucially, that doesn't mean that your neural net can represent that optimal discriminator. So this is kind of more in the case where you have a very, very expressive function, and we can just not worry about parameters and just characterize the function that would be the optimal solution. So what I'm going to claim is if d star of x is equal to p of x divided by p of x plus q of x, then the derivative will be 0. So I'm going to plug this expression into the derivative above and show that it actually works out to 0. So an expected value is just a sum over all possible x's of the probability times the quantity inside the expectation. So the expected value under p of 1 over d of x is just a sum over all x's of p of x divided by d of x. So I will plug in that d star expression. Since d star is p of x over p of x plus q of x, 1 over d star is p of x plus q of x divided by p of x. And that's all multiplied by p of x and summed over x to get the expectation. And similarly, for the second term, 1 minus d of x is just q of x over p of x plus q of x. So 1 over 1 minus d of x is p of x plus q of x divided by q of x. And that whole thing is multiplied by q of x because that's what we take the expectation under. So now you will notice that in both expectations, the denominator and the distribution with respect to which we're taking the expectation cancel out. So we're just left with a sum over all x's of p of x plus q of x minus a sum over all x's of p of x plus q of x, which works out to 0. So that means that this expression, d star of x, is in fact the optimal classifier that we can get if our positively labeled points come from p of x and our negatively labeled points come from q of x. Okay? And this is called the optimal discriminator or the Bayes optimal classifier. So taking p data to be p and pg to be q, we can derive the optimal classifier d star g as a function of g, where pg of x is just the distribution we get by sampling z from p of z and taking x to be g of z. Okay? So if g is fixed and we optimize the discriminator convergence, if our neural net is very, very expressive, in the limit, this is what we should get. We should get d star of g of x to be equal to p data of x divided by p data of x plus pg of x. Okay, so now what's the objective for g? Well, what we can do is we can simply plug in d star g of x into the min-max optimization of above and turn it into just a minimization over g. And again, I emphasize that this is purely a theoretical exercise. This is not how we would actually code it up. We would code it up using the approach I showed before. The only reason we're going through this is in order to understand what the GAN objective really is. What is the GAN actually trying to optimize? Okay, so if we substitute this in, we basically just have to write out v of d star g comma g, which is entirely a function of g now. Okay, so that has two expectations. An expectation with respect to p data, where we'll just plug in that expression for d star that we have up above. So it's an expectation under p data of log p data minus the log of p data plus pg. I just obtain it by taking the log of the expression for d star g up above. And for the second term, it's an expectation under pg of log pg minus log p data plus pg. That's because 1 minus d is pg over p data plus pg, and this is just the log of that. Okay. If the algebra here got a little too messy, feel free to pause the lecture and go over the slide to make sure that the algebra really makes sense to you. Okay, so here's the expression that we arrived at. It has these two funny expected value expressions. Do they actually mean something? Well, let's define another distribution that we're going to call Q. And Q is just the average of p data and pg. So we'll define Q of x as p data of x plus pg of x divided by 2, just the average of them. And then we can write our expression for the generator objective as the expected value under p data of log p data minus log q plus the expected value under pg of log pg minus log q minus log of 4. The reason that we get the log of 4 is because of the 1/2 term, right? Because if you have log p data plus pg, that's equal to log p data plus pg over 2 plus log 2, right, for the denominator. Now, the log 4 we don't care about because it's just a constant, so that's just to account for the fact that q is an average. Each of these terms you might recognize from our discussion before as a KL divergence. So anytime you see an expected value under one distribution of a difference of logs, that's just the KL divergence, which is a measure of discrepancy between two distributions. So This means that the generator objective is the KL divergence between P data and this average distribution, plus the KL divergence between PG and this average distribution. It turns out that this expression is actually another divergence measure called Jansen-Shannon divergence. And if it's named after two mathematicians, you know that it's going to be serious stuff, right? I'm sorry, I should say Jensen-Shannon divergence. The Jensen-Shannon divergence has some interesting properties. It goes to zero if the distributions match. So if P data and PG are exactly equal, then both of these KL divergences will go to zero, which means the Jensen-Shannon divergence will go to zero. But unlike the KL divergence, it's actually symmetric, which means that if you reverse the order of the arguments, you get the same value. So it's just another measure of the similarity between two distributions, a slightly different measure than the KL divergence that we typically use, but still a valid measure of similarity between two distributions, and that means that if we actually optimize the generator to convergence and everything is very expressive and we don't overfit or underfit, then we will in fact match the two distributions perfectly. So that's pretty cool. What I would recommend to all of you is to make sure that you can follow along with this derivation. This kind of derivation is important because for a lot of the more advanced stuff that we would do with GANs, this kind of analysis basically serves as the starting point. But for now, the takeaway is that this means that the GAN really is trying to match the data distribution. Okay. A small practical aside about GANs. Following all the derivations that we had so far, the conclusion should be that the generator loss is the expected value under P of z of log of 1 minus d phi g of z, which basically amounts to saying let's minimize the probability that the image is fake. In practice, we actually often use a slightly different loss. We use the expected value under P of z of negative log d of g of z, which is the same as saying maximize the probability that the image is real. Now, these two things are very, very similar. They represent the same concept, they have the same optimum, but their gradients actually look a little bit different when you're very far from the optimum. So take a moment to think about why we might use that second loss. Why might it be better to maximize the probability that the image is real rather than minimize the probability that the image is fake? And of course, it's not the only approach. There are other variants too. So the reason that the second option is preferred really just has to do with the shape of the function log x and the function log 1 minus x. So what I have plotted here in the lower left, at the top is the loss function negative log x. So that's basically the shape of the loss function that we typically use. And at the bottom we have the shape of of log 1 minus x. If you have a very bad generator, then you're going to have a large loss value, so you're going to be on the left side of these two curves. If you have a very, very good generator, then you're going to be on the right side. You're going to have a low loss. So the trouble with the log 1 minus x, the minimizing the probability the image is fake, is that the gradient tends to be pretty small when the generator is bad, and then it becomes really steep on the right once the generator gets good. And we don't really want that because it's most important for the generator to learn very well when the generator is bad. Because if the generator can't make progress when it's bad, it's never going to get good. Whereas maximizing the probability that the image is real, just because of the shape of the log x function, the gradient is actually very big when the generator is bad on the left side, and then the gradient gets small once the generator gets really good, so then it can converge to a nice solution. So that's basically why. It's just the gradients tend to be a little bit better behaved. Now, with that said, GANs have pretty ill-behaved gradients in general, and we'll talk about that a lot more in part 3. Okay, a few practical notes on GAN architectures. How do you actually set up the GAN? Well, here are some made-up architectures that you can consider. You could have a fully connected architecture. So you could basically take your Z's and map them through, let's say, 2 fully connected layers with 512 units each and produce an MNIST digit. And then you could have your discriminator also have 2 fully connected layers of 512 units each and produce a true-false output with a sigmoid nonlinearity at the end. Okay? That's a very simple classic architecture for a fully connected non-convolutional GAN, which might be suitable for very low-resolution images like MNIST digits. Or you could have a more complex convolutional GAN, maybe similar in spirit to some of those VAE architectures that I talked about before, where you might have some transpose convolutions actually produce a higher resolution image, and then you could have a convolutional discriminator that produces your true-false label. Here's an architecture for a real convolutional GAN. This is actually big GAN. This is a very modern GAN that produces high-resolution images. Now, this architecture is much more complex, but it is conceptually quite similar to the one that I have at the bottom. So the main architecture for the generator is shown on the left. You take your Z, and then you split it into 4 parts. So you basically put a little bit of Z in at the bottom, and then you put some other parts of it later on. The small part at first is transformed from a standard kind of fully connected thing into a convolutional map, 4x4 by 16 channels, and then it's passed through 2 residual blocks. Each of those residual blocks themselves have multiple layers, and they also get additional Z channels passed in, as well as the class label. This is for class condition generation. In each of those residual blocks, each of the orange blocks, that's what's shown in B. So each of the residual blocks has kind of a little residual structure, so it upsamples them, does 1x1 conv, and then adds that to a stack of 2 3x3 convs. Okay, so it's kind of a complicated architecture, clearly required quite a bit of trial and error to build it this way, but the basic principle is the same, that it's going to be some kind of transpose convolution style structure. Okay, conditional GANs. What if you want a GAN that generates, let's say, images of a particular class? Well, all you have to do is you have to concatenate your class label, shown here as Y, to both the input to your generator and the input to your discriminator. So you take your class label represented as a one-hot vector and just concatenate it to Z, and then for the discriminator, concatenate it to X. So here are some images from kind of the classic conditional GAN paper. This is MNIST digits conditioned on the digit identity, so you can see the top row is zeros, the second row is ones, the third row is twos, and so on. So that's how you can train a conditional GAN, very simple. A slightly more advanced GAN architecture, and this is the last one that I'll cover, just kind of for your understanding, is the cycle GAN. There are many, many different kinds of GANs, but I wanted to mention this one in particular because it kind of has a nice idea that I think also helps to illustrate how GANs work. So the cycle GAN is concerned with a very particular problem, not just generating any image, but specifically translating from one domain into another. So for example, if you get a large collection of photographs of zebras and a large collection of photographs of horses, can you turn a zebra photograph into a horse? And the problem is that you would be given these images, but you won't be given pairs. So it's not like English to French translation where you get a sentence in English and the corresponding sentence in French. You just get one collection of horses and a different collection of zebras. It's perhaps most obvious to see why it's important if you consider the example on the left, translating Monet paintings into photographs. You can find lots of photographs, and you can find lots of Monet paintings, but you can't find photographs of the actual scenes that Monet painted, because color photography didn't exist at the time. So this is what the GAN can help with. What the GAN can do is it can learn to generate realistic Monet paintings, and it can learn to generate realistic photographs, and then you can try to put them in correspondence automatically. So here's the design. This diagram looks a little complicated, but I'll walk you through it. We have 2 conditional generators. One conditional generator turns X into Y. So it's conditioned on X, which might be a photograph of a horse, and its job is to generate Y, photographs of zebras. And a second generator, F, is conditioned on a photograph of a zebra, and it produces a photograph of a horse. And then you have 2 discriminators. Discriminator DX just looks at an image X and tries to guess, is it a realistic horse? So this is what's going to supervise the generator G. And the discriminator dy looks at an image and says, is it a realistic zebra? And it's going to supervise the generator F. So dx is trained where positives are real pictures of horses, real x's, and negatives are generations from G. And dy is trained where positives are real photographs of zebras, real y's, and negatives are samples from F. But of course, in order for F to generate a sample, it needs to be given some X. So F will generate a zebra given a horse. So now what we can imagine doing is we can train these 2 generators and 2 discriminators, And now we'll have a generator that turns horses into zebras, and another generator that turns zebras into horses. But we're not done yet, because nothing about this says which horse or which zebra you should generate. So the problem is, why should the translated zebra look anything like the original horse? So if we give this picture of a horse, we would like to get a zebra that looks like that horse. That's good, that's what we want. But the generator could just produce some arbitrary other zebra, because all it's trying to do is please its discriminator. The discriminator doesn't care that this new zebra is similar to the original horse, it just needs to be a realistic zebra. So that's where this other part comes in, the cycle consistency loss, and that's what's shown here at the bottom. The cycle consistency loss basically says that if I turn this horse into a zebra, and then turn that zebra back into a horse, I should get the same horse. And that's measured in terms of distance. Like literally the pixels in the image should be close together in terms of their absolute value difference. So that's what's illustrated by the middle and right picture. So in the middle, you take an x, you pass it through g to get a y, and that y should fool dy. But then if you take that y and you pass it back into f to get back another x, that new x, x hat, should be similar to the original x that you put in. Which is another way of saying that f of g of x should be similar to x. And that's what is shown in the first line of this cycle consistency loss. It's minimizing the difference between f of g of x and x. And similarly, the picture on the right shows the corresponding thing going the other way. So if you take a y, if you take a zebra, pass it through f, you get an x. That should fool dx. And when you then pass it into g, and you get back another y, y hat, that y hat should be close to the original y, which is another way of saying that g of f of y should be close to y. Okay? So that's the idea behind cycle GAN. Two GANs, one for each domain, and a loss that says if you map from one domain to another and then back, you should end up in the same place where you started. Okay, a brief summary of these ideas. The GAN is a two-player game, and this is the two-player game, the equation for it. We can derive the optimal discriminator, theoretically, and from this determine what the objective is actually minimized at the Nash equilibrium. So this is the expression for the optimal discriminator, and when we plug that into the GAN two-player game, we can derive an objective expressed in terms of G, and it is just the Jensen-Shannon divergence between P data and PG. Note that this does not guarantee that we'll actually find the Nash equilibrium. So this derivation just shows that if we find the Nash equilibrium, the fixed point for this game, it will minimize the Jensen-Shannon divergence. And now we can train either fully connected or convolutional GANs, and there's a lot of liberty that we have in terms of determining their architecture. So for a particularly complex architecture, you can check out the Big GAN paper, which I referenced on that slide. And we can turn horses into zebras with cycle GANs, and we have conditional GANs and all sorts of other GANs.